Yes, let's start. And take the 3 by 3 matrix here. It's okay. Our aim is to find the determinant of A. Look at this and the determinant. Yes, this one. And use the row expansion. Take the first row. Write the first row entry 1. It's okay. 3, 3, minus 1, minus 1. And write the and corresponding minor and sign of position, and also it's okay. So, and we know that this one is a sub 1 1 plus a sub 1 2 plus first row expansion 1 3 3, and we know that a j minus 1 a plus j minor, determinant of the minor. It's okay. So, and the first row entry 1, and take this one, sign of position this one. It's okay. Minus 1, 1 plus 1, and plus. It's okay. And so plus entry 1, write the determinant of the minor, and this one 1 2 4 5. It's okay. So next one, next entry, use a different color. Next entry of the first row, because use the first row expansion. So, and take the first row and a sub 1 2, and this one, look at the position of this entry, first row, second column. So delete first row and second column. We obtain the submatrix 0 2 2 5, this one, and multiply by entry here 3. It's okay. This one is 3, multiply by 3 3, but sign of position, this one, sign of position here minus 1 to the first row and second column, and gives minus 1. So this one gives minus 1, minus 3. It's okay. So sign of position, this one is plus, this one is minus, and this one sign of position here minus 1 to 1 plus 3 is a positive, and so plus entry minus 1. So we obtain minus 1. It's okay. So, and write the corresponding minor of the minus 1, and means take this entry and delete the corresponding row and column. We obtain submatrix 0 1 2 4 minor. It's okay. Any question here? Write the entry and multiply by the sign of position and corresponding determinant of the minor. It's okay. So we obtain 3 2 by 2 matrix here. And one, second one, and third one. 2 by 2 determinant. And so we know that how to find, compute the 2 by 2 determinant. This one is 1 times 5, 5, minus 8. This one. Multiply by 1. And then this one minus 3. This one 0. This one minus 4 times. Minus 1 times, yes. This one gives 0. This one gives minus 2. So, and we obtain the result. So we claim that this result not depends on the row or column expansion. Choose one row on other row and or any column, and we obtain the same result. Yes, let's see that. For example, and this one is first row. For example, first row contains 3 non-zero entry, 1 3 minus 1. So we obtain 3 2 by 2 3 2 by 2 determinant. But look at then this one, and take the same and the determinant, but choose the, for example, choose the and the different row. For example, choose this one, it will be better. What is the reason? Because look at this one. Look at this one. Choose this one. Second row expansion, it will be better. Because what is the reason? First entry 0. So, and we can omit this one. And we obtain only 2 by 2 determined. But here, and the number of 2 by 2 and 3 is okay. I think it will be better choose the second row. Because second row has a 0 entry. It's okay. So, and also we claim that we obtain the same result, not depends on this one. It's okay. So let's see that. Look at use the second row expansion here. Sorry, this one. Second row expansion. Enter right entry 0, 1, 2. And write the sign of position. Sign of position. But here be careful. Sign of position. How to compute the sign of position? We claim that always this sign of position of the this position is okay. What's the this one? This one is in the first row, first column. So minus 1, 2, 1 plus 1, and the even. So this one is positive. This one is positive. Look at this one. Minus 1 to first row, second column. So we obtain minus 1. So sign of position here, minus, and this one is plus. And so if, for example, this one is 4 by 4, and this one should be minus. And look at this one. Second row, first column. So 3, minus 1 to the 3, minus 1. So this one should be minus. So we get the rule. Which rule? And start with plus, and then minus, plus, minus. And the next row start with not plus, because this one is plus. So, and minus, plus, minus, plus. And the next one, yes, plus, minus, minus. And the next one, minus, plus, minus, plus. This one is 4 by 4. If our matrix 5 by 5, and this one should be plus, minus, minus. This one is plus, minus, plus. It's okay? So, and let's come back here. Sign of position. This one is plus, this one is minus. So this one should be minus. This one is plus, this one is minus. It's okay? So write the corresponding minor. Now, yes. And this one is entry 0, entry 0. So delete this row and this column. So we obtain this one. 3 minus 1, 4, 5. It's okay? This one. So the next one, find the next entry. What's the next entry here? And the second row expansion. Next entry, this one. And delete the corresponding row and column. This one and this one. So we obtain 1 minus 1, 2, 5. It's okay? So the next one, catch this entry 2 to this one, delete the corresponding row and column. So deleted column, and then we obtain this one. This is okay? So we know how to compute the 2 by 2 determinants. Sorry. 2 by 2 determinants. Yes. So this one gives, yes, 0. So we can ignore this one. This one is 5 minus and minus plus 2 multiplied by 1. Yes. This one is 4 minus 6. It's okay. Multiply by minus 2. And then we obtain the same result. It's okay. Any question? No question, okay. So, but here, let's come back our determinant. Look at our determinant. Our question here, compute to this determinant. It's okay. So, and the previous, first of all, and choose the one row or column. And it will be better, and if the matrix has 0 entry, choose the second row. It will be better, this one, because we got the 2 by 2 determinant. Or another way, and choose the column, because we know that, choose the column, use the column expansion, we obtain the same result. This the column contains 1 0 row. So use the column, first column expansion. Look at this one. This one is by using the first column expansion. First column expansion, write the all entry of the first row. 1 1 0 0 2 2. It's okay. So write the corresponding minor sign opposition, first of all, plus minus plus plus minus plus, and write the determinant of the minor, and means delete this one, we obtain this one, and take the next entry of the first column, this one, delete the corresponding and the row and column. So we obtain this one. And also the next entry of the first column, this one, first row and the first row and the last column, delete. And then we obtain this submatrix. It's okay, this one. So let's compute. So, and we have 0 entry, so we can ignore this one because 0. So this one gives 5 minus 8, this one. This one is 6, minus and minus plus 1, multiplied by 2. This one gives minus 3. This one gives this one. So we obtain same results. It's okay. Any question? Okay. Now let's give this some properties, okay? Because sometimes it is not easy to get the determinant of A. It's okay, this one. And so using this property, so it is easy to see the result. It's okay. So let's give the property of determinants now. It's okay. And what's the determinant of if we know the determinant of A, what's the transpose of the determinant? It's okay, transpose of the determinant. So we claim that this one is equal to this one. What's the reason? Because take the determinant of A. It's okay. And so how to compute this one? Use take the any row or column. For example, choose this row. Using the row expansion, our aim is to get the result. But what's the transpose of A? Transpose of A means interchange row and column. So look at this column, this row. This row and is the corresponding, for example, this one is row I and this one is column I, the same, because transpose interchange row and column. It's okay? Now, and this one. So, and here, and use, and this one is row expansion here, and the row I is okay, row I, and here, and use the column column I. It's okay. Column expansion use. So we obtain the same result. It's okay. Determinant of A is equal determinant of the transpose. Because this one we get this result by the definition of the and transpose matrix and determinant. It's okay. Definition. So, and also the second property, if our matrix has a zero row or column, what does it mean this one? Zero row and means all entry zero. So means, and look at this and this example, and the first row contains zero entry, all of them zero, and it's called the zero row, this one. So, and compared to this determinant, of course, choose the one row or column, but it will be better choose the first row because all enter is zero and multiply, and this one is 0, 2 by 2 determinant, minus 0 times 0, this one is 0 times this one, 0, 0, 0, so we obtain 0. It's okay? It is easy to see that. And so, and of course, this one is valid, and the for and the column, if our matrix contains zero column, so we obtain and the zero, because what's the reason? Because choose this column, use the second column expansion here, so we obtain 0. It's okay. So no computation, and then we obtain result because then our matrix has a zero row or column. It's okay. So the next one, next property, and we have one matrix A, and we have another matrix B. It's okay here, and then but and the B is a matrix. B is obtained from A, and means take the start with A. It's okay. If use the and the sum and the operation, which operation here? Choose the one row of A. For example, choose this row. This row. It's okay. Choose this row, and then multiply and take the any real number K and multiply by K. It's okay. So this one is row equivalent to another matrix. It's okay. This matrix. So, and the new matrix is called, for example, here B. So, and the question here, and what is the relation determinant of A and determinant of B? It's okay. What's the relation? If and the B can be obtained from A, how to obtain? Multiply by K and the one row, and then we obtain B. So what is the relation here and the between and the determinant of determinants of A? Determinant of A and B. It's okay. So we claim that here, for example, we don't know and this entry and this star. If, for example, compute to this determinant of A and using to this row, it's okay. So, but multiply by K here, and this one is K star, and K star, for example. And how to compute determinant of B? Use the same and the row expansion. So look at this one and this one. Only we obtain K times determinant of A. It's okay. This one is important. It's okay. So, and they look at this example and they take the 3 by 3 matrix. It's okay. And they take the n scalar and determinant this one, and they take the k scalar, and means this one is equal, choose the one row, it's okay, multiply by this one, it's okay, this determinant, or and this k multiply by the any column. So this determinant is equal this one and this one. It's okay. Let's see that this one. Take the easy example. It's okay. simple example. 2 by 2. Take the 2 by 2 matrix. Look at this one. It's okay. And our aim is to compute the disdeterminant. What's the disdeterminant? 3 times 5, 15. And the 2 times 9, minus 18. So we obtain minus 3. It's okay. But then the disdeterminant, we can compute this determinant by using this property. It's okay, this property. Take the same determinant. Look at the first row. First row contains common and the factor. It's okay. 3, 9 and the first row, and this one contains 3 factor. So we can write this one, use this one 3 times, and we claim that this determinant is equal 3 times this determinant, 1, 3, 2, 5. Let's see that. Our aim is to check that this one is equal this one. So this one gives 5 minus 6, and we obtain minus 1 multiplied by 3 minus 3. Look at this one. This one is minus 3. The same. It's okay. So yes, it is possible to write our determinant. If any row contains the same and the factor here, it's okay. It is possible to write this one 3 times this determinant. It's okay, this one. Or for example, take the same and the determinant. Look at this one, the last row. Take this one. It's okay. And we claim that, and we know that, and here this determinant is 3 times this one. It's okay. But here we claim that is equal this one. Take this scalar, multiply by, and take any column or row, multiply by this scalar, we obtain the same result. It's okay. Yes, our aim is to check that, and this one is equal this one. Let's see that. And multiply 3, 3, 6, 3, 5. This determinant is 15 minus and 18, and we obtain minus 3. Yes, we true. It's okay. If any row and column and it contains the same and factor, so we can write in this one. It's okay. K times this determinant, or contains any column contains K here, K times and the entry. So K can be written, and our determinant can be written in this form, K times and this determinant. It's okay. Any question? No question. Okay. So the next one, take the R matrix A. It's okay. R matrix A. So interchange and some operation. Which operation? For example, we have 3 operation on matrices, and the first operation start with A. It's okay, and use some elementary row operation. We know that we obtained another matrix P, but here be careful, not equal this one. Row equivalent matrices. Use some elementary row operation. Be careful. And take the matrices, only use row operation. Elementary row operation. Elementary row operation here, be careful, and row equivalent matrices is okay, not equal. So we have three operation. One operation, multiply by k. For example, choose one row here, multiply, so k star, and then. So what's the relation between determinant of A and determinant of B? It's okay. So, and we know that, and so this one is equal, and the k times, and determinant of b, sorry, this one should be this one. So b can be obtained and from a by and multiplying by k. So what's the relation? And the determinant of b is equal k times determinant of a. It's okay. This one. A is row equivalent to B, but and the operation type and this one. It's okay. So this one. This one is the first and the type. The second type, elementary row operation. Take the any row and ij. This one is row I. This one is row j. Interchange. So we obtain new matrix. It's okay. So and delete this one. Use the different color, row j. So interchange row I and row j, and we obtain the another matrix. It's okay. This matrix is called matrix B. It's okay. So we know that, and the A is not B. A is not B because and the change to and this one and this one, but A is row equivalent to B. It's okay, this one. But what is the relation if and the B can be obtained from A by using this operation, interchange row? So, and what's the and this one? We claim that and the determinant of B is equal minus determinant of A. What is the reason? Because use the and this row operation, expansion, compute the determinant of A, sign of position. But here and the row J, but row I and the row J the same expansion. It's okay. So, but determinant of B use the row J expansion and here row I expansion to compute the determinant of A. So we obtain this one. It's okay. Now, and this operation, and here this operation gives this one. It's okay. Row equivalent matrices. What's the relation and between determinants? It's okay. This one and the row equivalent. This one. It's okay. So what's the next operation? But be careful in here. But determinant, row and column, and this property valid for columns and also. It's okay. Column operation and means take the this and the matrix, this matrix and this column interchange. So and the determinant minus this one. It's okay. This one. So let's see that this property is valid for matrices. Take then the simple example, this one. Let's compute to this one, and we know how to compute. This one gives this one, and but here interchange the row, first row and second row, so we obtain this matrix. But you don't have to compute this determinant because we know this and the property. If we know the and this matrix is 11, this one should be minus 11. Let's see that this one is true or not. Interchange row and we obtain this matrix B. This one is matrix B and this one is 10. This one is 21. So we obtain minus. This one is determinant of A. This one is determinant of B is equal minus determinant of A. It's okay? Or change the column and we obtain the same result. It's okay? So the next one, if our matrix contains the same row and column entries, it's okay? And the two rows or columns are equal. So means if take this this matrix, our aim is to compute the determinant, but this one and this one contain same entries, okay, are equal. So we claim that this determinant is 0, should be 0. It's okay. Or row or column. This one is valid for columns. It's okay. If we have two and the same column, it's okay, are equal, then determinant of A is 0. Let's prove this one. It's okay. And for example, take the matrix A, for example, and the row R and S are equal. It's okay. And take this and this one, row R, row S, the same. It's okay here. This one and this one. It's okay, are equal. So interchange and these rows. It's okay, interchange. So, and we know that use this property, previous property, if interchange row and we obtain and the same determinant but multiply by -1. So, and the -1 times determinant but interchange row R and S. So, and this one and this one. But we know that these row and this row are equal. So, and this one gives the same determinant because and the same and the determinant of A. So, we obtain determinant of A is equal minus determinant of A. We know that determinant of A any real number, this one is real number, but the same real number minus. So, what can you say about these real numbers? Sorry, there's a problem here. So, and what's these real number? For example, alpha is equal minus alpha, and alpha should be 0. Otherwise, we get contradiction. It's okay? Yes. This one is sorry. This one is our matrix A, and this and the row is equal to this row, and interchange use the and the previous and the property if interchange row and column multiply by -1 times this one interchange, but and this determinant is equal determinant of A because the same. So, and determinant of A is minus determinant A. So this one is real number. So these real numbers should be 0. It's okay. This one is not. So, for example, look at this example. This row is equal to this row, the same. So this one is minus. Interchange, and then we obtain minus determinant minus, and so 0. Or look at this one and this column is equal this column, so means and this determinant is 0. It's okay. So another operation, elementary row operation, start with A. It's okay. We know that this determinant and some operation, the last operation, elementary row operation, take the one and the row I, another and the row J, take the row J. It's okay. This one is row J. It's okay. What's the operation? The last operation, elementary row operation. Take this one, multiply by k scalar. It's okay. K scalar. But be careful and let's come back one property, which property? This one, k, multiply by k and this one, but here k should be non-zero, because otherwise, and the every and the determinant of the and the every matrix is zero, multiplied by zero. It's okay. But here, no, it's not true. Sorry, any real number here. This one is any real number. Sorry. This one is any real number. Yes, this one is okay. No gap. It's okay. Let's come back. Yes. The last one. Yes. Sorry. Last one, take the matrix A. It's okay. Matrix A. And the row I. Take the row I and row J. And here, and use the last operation, last type, elementary row operation. Choose row I, multiply by K, add to the row J. And so we obtain new matrix is not equal A because row equivalent, not the same. So, and we obtain matrix B and such that, but the row I the same, but and the row J is multiplied by this one, K times this one, and the corresponding entry, this one is okay. For example, this one is star, K times star plus, and this one is B, for example, B, and then it's okay. Multiply by K, add to this column. So what can you say about the relation and the between and the B and K and the determinant of B, determinant of A? It's okay. What's the relation? And here we claim that B can be obtained from A by adding to each element of I, and this one, row or column. These property valid also for columns. It's okay. A constant K, this one, and times the corresponding element of the J row here. But here, be careful. A is not J. It's okay. Not the same and the row take. It's okay. And row I and row J. And use this operation, we claim that determinant of B is equal determinant of A. This one. It's okay. So let's see that. And this one is take this determinant. Let's compute. But and I think our aim is to get and the more zero and then choose the one and the row or column. But this column such that contains and the more a lot of and the zero, so it will be easy to compute. For example, you look at this column, choose this column, we obtain 2 by 2 determinant, and this one and this one is okay. The number of determinant 2 by 2 and the 2, because this one is 0. It's okay. 0 times this one we can ignore. And so, but our aim is to get more and the 0 in the first column. So how to get first to get 0 here? So use the sum operation, elementary row or column operation. It's okay. So which one? Use and this one. Take this row, multiply by -2, add to the first row. It's okay. Let's see that. And this one is the last property. This property is okay. We know, and if use this property and determine this operation, determinant of B is equal determinant of A. So let's see that. Let's see that this one is okay. It will be better. And so multiply by -2, and then we obtain 0 minus 5 minus this one. So compute to this one. Ignore this one. Sign opposition plus and minus. -1 times, yes, -5 minus this one to 1. Yes, compute. It's okay. Same. Yes, this one it is important because our aim, for example, take 5 by 5. 5 by 5 matrix. How to compute 5 by 5 matrix? And start with this one, for example, take, yes, 5 by 5. So choose the one row or column and then write the determinant. So, but entry, these and what's the number of entry? 5. So we obtain 4 by 4 and the determinant is okay, but the number of and the determinant 5, and every 4 by 4 gives 3 by 3 determinant. The number of 3 by 3 determinant is 4. We have, and first of all, we have 5 4 by 4. Each 4 by 4 gives 3 by 3. And then every 3 by 3 gives 2 by 2. And the determinant, the number of determinant of 2 by 2, 3. And so we a lot of and you have to compute a lot of and determinant. But if we use this property, this property is okay. So our aim is to get more zero. Apply this operation. Maybe we get and zero here, not zero, and so use some operation we get zero. So we obtain only one 4 by 4 determinant, not 5, the number of 4 by 4, 5. It's okay? So we obtain only, because only one non-zero entry here. So, and we get 4 by 4, one 4 by 4 determinant, the others because 0, 0, 0. And then, and choose one column or, and this one. If we get all of them 0 and the one non-zero, so, and this one is, yes, this one gives only one 3 by 3, and use some operation to get 0 more, and then only we get 1 2 by 2 determinant. It's okay? So, yes, these property, these operations, it is important because and the less computation. It's okay to compute and the determinant and 4 by 4 and more, and the dimension greater than and the 5 by 5 maybe. It's okay. So, and this operation useful. It's okay to get determinant. Any question? No question. Okay, and one more, and the property, take the matrix, but upper triangular matrix. Upper triangular matrix in this form. It's okay? This part is 0 only. So what is the determinant? We claim that determinant of A, and this one is A sub 1, 1, A sub 2, 2, main diagonal at N sub N, N. This one is 0. It's okay? We claim that this determinant is equal. Look at the main diagonal. So, and the determinant, the product of the main diagonal entries, A sub 1, 1, 2, 2, and N. It's okay? And also, this one is valid lower triangular matrix and this matrix. Look at the main diagonal entry, and so the product of the entries on the main diagonal gives the determinant. It's okay. So we obtained some result of this one. Take the diagonal matrix, because we know that diagonal matrix also lower and upper triangular matrix is okay. So use this property. So we can say that determinant of the diagonal matrix is the product of the all entry, its main diagonal. It's okay. And also last property, take the two matrix A and B and compute the product, and then we obtain the same, we obtain the new matrix. So question, what is the determinant of and this one? And we claim that, and the determinant of the product is product of the determinant. It's okay? This one. Okay, let's stop here. It's okay. Any question about the property?